Well, hello guys! Today we're going to be taking a look at internal energy. You know, the energy that lives deep inside of Jace and motivates him to go ahead and learn about thermodynamics on his own. So let's get going while we're all still so motivated. By the way, I should let you know real quick that in today's explanation of internal energy, we're going to be using ideal gases to illustrate the topic. So it probably wouldn't hurt if you had a rough idea of what an ideal gas is supposed to be in the first place. If you do, then we can go right ahead and get started. Okay, with internal energy, the important thing isn't necessarily where you find it. It's much more interesting to know what it's actually made up of. Essentially, internal energy is made up of three parts. The first part is going to be thermal energy. If you were paying attention in class at just the right time, you might have picked up on the term Brownian molecular motion. The motion referred to here is nothing more than incredibly chaotic behavior of the atoms and molecules that make up a substance. Like a gas, for instance. The molecules in a gas fly around aimlessly, smashing into each other, against walls, whatever. If we take the average value of all this chaos, we get what's commonly known as temperature. In thermodynamics courses, this part tends to be the one that gets all the attention, to the point that the next two often get neglected. Another part of internal energy is chemical energy, which is pretty much nothing more than the bonds between the molecules. I mean, you know there's something holding the molecules together, and this energy part is part of the chemical part of internal energy. So yeah, there isn't much more to say about the chemical part, and the same goes for the third part, which we call electrical energy. This refers to anything that has to do with electrical charges and differences in electrical charges along with the motion of electrons. Well, that's cool and all, but what do we need internal energy for? As you might easily imagine, it's insanely difficult to determine the internal energy of a substance. You've got to be able to measure the various parts with absolute precision, and that would be a real headache. Lucky for us in thermodynamics, the actual internal energy of a substance isn't something that really matters all that much. What we're really interested in is the change in internal energy, and we've got a pretty convenient formula for figuring this out for ideal gases. This is the whole thing right here. The du represents the change in specific internal energy. By the way, specific just means that we're looking at the internal energy per kilogram. So if you have 8 kilograms of an ideal gas, you still have to multiply the equation by 8 kilograms. The CV here stands for isochoric heat capacity of the ideal gas in question. Note here that while heat capacity is often assumed to be constant, it doesn't necessarily have to be one. Just make sure you read through the problem carefully, okay? Isochoric warming capacity simply describes how much energy you need to put into the gas in order to raise the temperature of it by 1 degree. Oh yeah, and the last part is the dT, which stands for the change in temperature. This is actually pretty easy. It's just the difference in temperature before and after a process. The cool thing here is that the internal energy of an ideal gas depends on the temperature alone, since heat capacity is often taken to be a constant. So if there's no change in temperature, we know there's no change in internal energy either. This is a really cool thing to be aware of, and we're going to need to use it a lot when working with the first law of thermodynamics. So let's go ahead and sum this all up. The internal energy of a substance is essentially made up of three parts: thermal energy, chemical energy, and electrical energy. The one that we're most concerned with is thermal energy, but we're also not all that interested in getting an actual value for internal energy. What we really want to know is how much it changes. And finally, here's the formula for determining the change in the specific internal energy of an ideal gas. What this tells us is that the internal energy depends on the temperature. Sweet, so now we've totally got this. But we're not even close to being done yet. See you real soon in the next video.